let's get started. So I guess we can get started for today's lecture. So I guess people still coming in. I know the traffic is not easy. So we will slowly review what we have been doing, and because I know this topic is, as I said, one of the milestones of this class, which is probability modeling. So I want, and also last time we do the U reply, we see that many of you asked me to slow down a little bit. So I think it's good to have a brief review what we've been doing. So the idea of random variable is usually the way that we model uncertain event, right? Because we're looking at stock price, right, stock market, or looking at how many people coming, how many consumers are buying the good, how many people like your stuff, so on and so forth. And the way to model it, right? If you use topic 2, the probability, we don't know how to do, right? Unless a lot of data, right? But and sometimes data can't cover a lot of stuff, right? We just cover the data that, I mean, is representing the things that we collect data on, and we want our conclusion data to generalize to a situation that we haven't done it, right? That is the idea of random variable, right? Because when we learn today, we talk about, right, binomial and Poisson and hypergeometric, right? Those things that are can be applied in the practice, and that is the reason why we want to study those. Okay, so maybe very quickly we review, and today we will talk about continuous random variable exponential. Probably stop at normal, but we'll cover the things at normal at the end this week. But let's very quickly review what we've been doing. So again, we start with random variable, and random variable is simply consider random experiment, their outcomes, and then we are trying to give numbers to outcome. And you can imagine this number is just kind of measurement, right? You're measuring, right? The amount of rainfall, number of people coming, right? Number of people coming is a measure of how much they spend, right? Is the idea, right? Just measuring, and it's kind of simplifying sample space. The reason is being, as we have mentioned many times, is a toss and coin, right? It's a head or tail. And of course, you can do a model for that, but with that number, sometimes it's hard to work on. And we quantify the outcome, right, of the random experiment. And that is of course, there's a kind of simplification, right? Like this, like head or tail, 1 or 0, there's no loss of information, right? Because every outcome is mapped to a number, and the number is meaningful, right? And when you consider total coin twice, okay, we can convert it from 4 possible outcome to number 0, 1, 2, right? It's a collapsing from 4 to 3, right? And this meaningful if this collapsing has meaningful meaning, which essentially here in this example, we just collect total number of heads. That means that we don't care about the order of the outcomes, right? It's head, tail, or tail head are the same, right? And there's a benefit of doing it is in the classical world where usually you consider each outcome is equally likely, right? But then your last number of outcomes. But now we consider the number of outcome strings, right? Suppose you toast it 10 times, right? And number of outcome in the sample space is 1,000, but we may collapse to 0 to 10, right? Only have 11. By simplifying the number of possible outcomes, right? Because we do random variable, the support is much smaller, but the probability will be much more complicated, okay? But there's a benefit of reducing the sample space, right? Right. Is you can imagine the sample space originally is 4 outcome, but the sample space becomes 0, 1, and 2, right? But that is, you can think in this way, but that's the idea. Okay, that's the idea. And you can do the same if it's continuous. It simply means it's a many of them, right? And Usually when I talk about finance or kind of measurement, the real number, that is the continuous random variable. Okay. And very quickly, the description of the discrete random variable, because discrete you can count them, so which means that for each value you can put a probability on it. Okay, that is called probability mass function, right? Because usually the classical sense is each outcome is equally likely. That is a uniform distribution, so that this function is not really useful. That's why we don't talk about this last class, right? But when we talk about when we simplify the sample space, then each outcome no longer equally likely, right? So for example, like this, right? Head or tail is equal, then the p function, right, is 1/2, right? But when we talk about like this example, when we toss a coin twice, then no longer equal for each one, right? Because 0 and 2, right, responsible for head, head, or tail, tail, right? But 1 will be head, tail, or tail, head. Actually, will correspond to 2 outcomes, even in one number. So that's why the p function will look like in this form, right? This bar chart is very useful to visualize what you're doing, right? And actually, this collect the data, right? If you repeat doing the data, the probability should be the relative frequency, right? And the other way to describe this is the big F, right? The big F, the P are equivalent, right? You just stacking the P will become the F, right? Or de-stacking the F, you get the P. Okay. So either we call the this PMF function or the CDF function are equivalent thing. And of course, usually just PMF, that's the matter, right? Then why we care about this big F? There are two reasons to focus on big F. One is being, when we talk about continuous one, that will be the same thing. So we want to draw the similarity between P and F. We talk today, the continuous, the small f and big F. That will be the reason, because the continuous, this one is the primitive, okay? The primary thing to study, right? Because for discrete, this is the thing we want to study. For the continuous, this is the main thing we want to study, okay? And secondly, as we see the example, we often find the F is very useful, okay? And probably as we see the Poisson example we have seen is number of customer no more than what is something we care, or more than what is something we care, right? It's usually the question that we actually ask is the big F. And actually you will see from Excel function, I actually have the big P and the big F already Excel built in. So you don't need to worry about this calculation. Of course, it's complicated, but everything is built in the Excel. So then you know the formula, that would be good. The next two things is, once we know the P, right, the big P, actually we know how the future looks like, right? The bar chart tells us how the future would expect to be, right? Because remember, probability is quantifying future uncertainty, okay? Just to remind you, what is probability? Probability is our prediction or our educated guess or what we think what might be happening in the future, right? And as we learn, and topic 1, mean and variance, actually that's a good summer statistics, right? That can be used to also for us to summarize the random variable, right? Because you can imagine we run the experiment many times, then every time we have an outcome, an outcome can become a number, right? And that number we can look at the average, right? To give a precise idea, right? Remember, suppose we roll a die, right? And we roll a die, then each time we have a number, right? And then you run many times, there are many numbers. And also we can find mean and variance, right? And the idea with the mean and variance will be expectation and the variance idea. And probably you ask why we do that, because expected value will be our educated guess if you give me the P, right? Suppose you give me P, right? You tell me, okay, this is our quantification of the future. I think X will be equal to that value and that value with this probability. But you want to give me what would we expect to be, right? One number, that will be the expected value, right? There's a number that represents the random variable, if you ask me, right? That would be the case. And similar, the variance will be just give us the idea how variation of this random variable compared to the mean, right? And that's why look at the finance application, expectation will be about our expected return, right? Variance, the risk of your investment, right? So that's why when you try to learn finance class, they will try to look at the investment to try to make the portfolio, make the expected value portfolio as large as possible. At the same time, minimize the variance. Okay, you will learn this when you learn 3000 finance class. If you want to study investment class, they will spend, at least half of the lecture, half of the course to study those. Okay, but it's not the concern for us. Okay, but the thing is, what I want to tell you, right? This is the idea. There's some property there. Just to remind you very quickly why this is useful. Linear property is when you look at your portfolio consists of A shares of stock X plus B amount of cash, the expected value of the portfolio will be A times the expected return for single stock plus B. Okay, so that means that we can do divide and conquer, right? Makes things easier. The proof behind is in the black. You don't require the proof, but this is the formula that we use, and I think I add the example here to illustrate how it's being used. I'm not going to repeat that, but you can try to read it. It's not something complicated, right? Suppose the price of stock is 1, 2, 3 with this probability. Then you want to look at the portfolio. We have 100 shares of stock X and with 300 cash. This is the formula. Okay, I don't think I need to talk too much about that. Similar to variance, right? The idea is looking at how the value different from mean. I think I illustrate this from this example, and I also include the portfolio variance application. So I think that would allow you to realize how important is this. And of course, we are not finance class, so I'm not too anxious about this point, but just to illustrate why we care about mean and variance, right? Do remind you yourself what's mean and variance. Mean is a number that represents the data, right? So this is expectation. It's just a summary. It's a number to represent the random variable. You give random variable, you describe it by the P, right? The P is a very complicated object, can be the bar chart, can be very complicated. If you want to give me one number to represent the P, that is the expected value. And you ask how representative the P, the variance. Okay, that's no different from what we learned topic 1 and topic 3, right? That was the same thing. So everything is well connected to each other. Okay, and you learn the property here, right? And here we just try to scratch a little bit surface of how do you extend from one variable to another. Okay, and we just slip through under the rug. We'll come back to this covariance idea somewhat in the regression, although we don't explicitly use it, but I don't think you have difficulties if you imagine that the sum of the expectation will be equal to the expectation of sum, okay? And the variance, if they're independent, is sum of the variance, okay? And these are the two things that we will needed for next week onward when we talk about sampling distribution, okay? This expected this formula, when the independence, add them together, just adding their individual variance, okay? This is the formula that we'll be using, and this is the reason why later you will see this is the reason why doing sampling will be useful, okay? If there's no formula, we cannot do any sampling, okay? Later you will see. And lastly, this is the formula that I want to emphasize, but of course is beyond the scope of a class, is the two covariance. This is very important idea. If they're not independent, the formula is way more complicated, because look at the sum, right? X and Y, you need to take a look into how they move together, right? Because if X go up and Y go down, the accelerator cancel out, then variance will be 0, right? And just go back to the idea of old wisdom of never put all the eggs in the same basket, right? If they put the same basket, the covariance is 1, right? They all break and they all don't break, right? If you separate into multiple places, that covariance will be 0, right? Or even negative, right? Depends on how things you would do. But that is the reason we learn diversification in the finance idea, right? You want to diversify your risk, right? If one company goes up, the other doesn't affect it, right? And then you diversify across different industry, across different region, across different stock market, right? Across different finance instrument. That's the idea, right? But we're not going to that. But I think it's good to now I go slower into these 4 or 5 examples that commonly use. And of course, if you want to learn more detail how to do this, learn more than many you can do, at least 10 to 20 you can learn. If you want to go further, of course, there can be one whole class just to trying to study this kind of probability and how they work out. You go to a class called probability modeling. You study the whole class to learn, whole course to learn this. Okay, 13 weeks to learn this kind of stuff. But we just scratch the surface and try to talk about things that will be useful. Okay, and the uniform, although is probably the most naive one, you just assign each outcome equally likely, right? And the n of them is 1/n for each. And this is usually the basis point of we try to do modeling without knowing what to do, or that's a naive one. And if you learn machine learning, that will be the thing that we start first. And the machine will start to learn. How to learn. The one way is what you learn the base rule. You can update, right? And then that is the way that it can be done. But uniform is the standard way when you don't know what to do. And base rule we keep updating and change the p. Okay. And the next one, this is something that will be the most useful one when you talk about binary data, right? You ask yes/no question, or the future if you consider is success or failure, right? It's just like the sample size is very complicated, okay? But for us, it's just like we just look at the binary outcome, success or failure, whether you like it or not like it, right? Whether you buy the good or not buy the good, okay? It's a very simple idea. And a lot of the time, the data is just like binary, yes or no, right? Do a survey, do you like this? Do you like that? Do you want to buy it, right? Because this is the idea, okay? And in the upcoming half of the course, actually we'll do a lot of binary data, okay? Besides continuous data. So that the two things is this is the binary outcome, okay? And for binary outcome, it's just very simple. Just success is p, failure is 1 minus p, okay? And we use because it's number of success with natural 0 and 1, right? And this is the function we have, right? This is a table that is relevant, right? And of course, this is the standard way. And then you look at textbook, it's often written in this form, but that's no different from the form that we have seen in the table. The reason they write it is because it's consistent with the binomial, okay? And then there's nothing deep, but same as this guy, okay? And as we said, mean and variance is summary statistics, right? So besides on the p, if you want to summarize, you want to give people mean and variance, that is the thing you give, right? So I hope that is clear why we care about the big P and we care about expected value and the variance, okay? And this is the basic thing you want to learn, right? When you learn a distribution, you want to learn how the big P looks like and what's the mean and variance. Of course, you want to learn, of course, you may ask, wait, why don't I talk about skewness and kurtosis? Yes, that's correct. But the thing is, we're an elementary class, right? If I talk about skewness and kurtosis, probably you will kill me, right? So this is the thing we just need to do. I mean, if you look at Wikipedia or other things, they will tell you the kurtosis and skewness. But this is an elementary class. We just okay with the expected value and the mean and the variance. Okay, that's sufficient for our purpose. Okay, I mean, definitely go to kurtosis. You can go to skewness. That's no problem. But that's not the goal of our introductory class. Okay, and then also give an idea. Although we don't talk about this, right? We learn mean and variance. That is how you use the model. Because the data you can obtain from the historical data, you can look at the mean and variance, right? And look at the mean and variance, you can have idea what should be the p, right? For example, the example is look at the case of how many people like spicy food, right? And you look at the historical data or a survey that give us the value of p. Right? And then that is how we try to apply it to a known scenario, right? Because say suppose look at how many people in United College here like the spicy food. right? And then give you the P, right? And this P you can use it for estimate for the P for the CHK, right? That's the idea. But of course, in our class we don't talk about this. Probably we talk about this because binary data we talk about this. So you will see how this actually work in practice in our class. So this will be we actually do this, okay? And of course, this generalized idea of binomial is asking us, in the case of the future, actually is the binomial is tossing a coin once, is just asking us toss the coin n times, each time independent. If you think the future is actually like this, okay, it's n toss, right, of independent coin, and asking we care about number of success is, okay, then this is the way to describe it. It's good enough. Then this is what you would do, right? You can imagine, right, a case of, say, you're at the hotel, right, and each guest may be using the restaurant, spend restaurant dinner in the hotel, right? The proportion. Then you can calculate how many people actually there using the hotel dinner buffet, right? Then you can see how much food to prepare, so on and so forth, right? These are the idea, right? I think remember the example here is the restaurant, right? And he gets 30% people like the spicy food, and then with that, you can imagine, you can model this as a binomial, right? And then he can then, by making a binomial assumption, you know the P, and then we can do a lot of calculation. Of course, you can calculate mean, you can calculate variance. I don't put it here, but it's easily, it can be done, right? Just by example there. And the formula is like this. I'm not going to talk about this because I think I've talked about this many times already. But you can see this is the useful to model. If you think the future, you know there's a n box to open or n coin to toss, and each coin is the same, right? That would be the useful one, right? And you can imagine this is exactly same as sampling with replacement, right? You have a 5 thing to sample, right? You take it out and put it back, right? That would be the idea, the same, okay? So this is the example as I mentioned, right? And I probably want to say about the application, right? Say, for example, you want to have marketing campaign. You want to estimate the probability of the campaign by calculating how many people purchases, for example, like this, right? The example would be, suppose you have a company who is going to send 10,000 leaflet to the to potential customer, and maybe 5% of them actually buy it, right? And then actually, then you want to say, okay, if this is follow binomial, which is fine because you assume each customer probably likely independent, and 5% from historical data, I think is fair. And then you can know how many people actually come to buy, right? You can find exactly 500 will do the purchase, and you can know any number, right? Then you can, by doing so, you can think about inventory management, or you can think about how much customer to target, right? So on and so forth, right? And if you want to achieve this kind of purchase, right? So that is the thing we can do further. Of course, as introductory project class, we cannot go further from this, but you can think about the cost and benefit, right? How much money you need to spend to do the advertising, right? Is it cost beneficial, right? Because different campaign can have different probability successfulness, right? Maybe doing this leaflet is 5%. If you do TV show, maybe 10%, right? So on and so forth. So you can see which advertising channel is used, right? And look at the mean and variance and all kind of stuff. You can do analysis, but this is not the cost for more detailed study. But you can imagine once you know the P, you make some assumption of the or you know more details of the data, then you can go further. Same as quality control, right? You can imagine that inspection, you want to collect 100 sample, and historical data tell us it's 2%, right? And you want to figure out exactly 5 are defective product, right? Because you want to have a quality control. You want to see whether this new product is going to be there, right? Because probably iPhone 15 Pro Max happen to be some quality control issue, right? And probably maybe, right? As Apple, they want to do some quality tests, right? And then probably based on this P, right? Based on the testing outcome, you can think about the base rule, right? To see whether the QC have to change how defect rate, so on and so forth, right? And based on this, you can imagine how the company should think about the Apple Care, right? Because say this company warranty policy, right? Then you can see how things can be done, right? So there's many things you can imagine as long as you think the futures model is a pros cons n times, right? Each pros and con as a probably P, right? The same. So that would be the binomial. Okay. And just to graphically, this would be like this, right? Because I want to talk about Poisson, that's good to think about this. If you think the future is like open a box, right? The box can be only 2 outcomes, right? One outcome is happy outcome. The other outcome is a sad outcome, right? P and 1 minus P. That is the binomial. Okay? If you repeat this 1 time, 2 time, 3 time, up to n time, right? Each time the same, still a happy phase with probably P, and sad phase with 1 minus P. Oh, the sad phase is wrong. Sorry, I should have consistent sad phase here. Okay, and in that case, if you think the future is like this, then it's a binomial. You can use it. Okay, and this is, we know the n and the p, then it's binomial. So what is Poisson? Poisson is asking the following: instead of n, we talk about time period. Okay, we talk about a time horizon. Okay, say suppose an hour, 1 hour. Okay, and we divide it into very small interval, right? We divide n interval, right? And we can imagine each interval, right, also have happy and sad, right? We probably P as happy and 1 minus P sad, right? And when n, we make the n is very, very large, right? The interval is so small, you're expecting P is very small as well, right? Because this interval is so small, right? And you can imagine that happy means someone coming, right? Happy maybe a restaurant, someone come, or happy is something happened, right? Maybe typhoon hit Hong Kong, right? No class today, right? Unfortunately, we are not successful. At least in the morning, is no class, but unfortunately, you can't enjoy that. And that's the idea, right? That's the Poisson. Within a period of time, right? How many successful case, right? And we'll call this NP is lambda, because this is what that matter, right? And tau lambda is the mean, right? So that's the Poisson, right? Poisson is simply different time period, right? How many cases of successful things will happen, and the average of this is lambda, okay? Then turn out, this is one interesting thing about the Poisson, is because P is very small, right? The variance is also lambda, right? Because when n is very large, P is very small. So NP times 1 minus P is 0 in the binomial. So that is the idea. I hope that's clear, because you want to model within a period of time what happened. That is Poisson, right? And one thing I have to emphasize, this main assumption in the Poisson is being that following the binomial, right, is binomial is independent, okay? So for Poisson to hold, it must be the case, which you have to assume for the moment, things happen in the, say, this is 1 hour, right? Suppose the mean is 10, okay? And even if the first 10 minutes, you have 100 people coming, okay? And what happened from the remaining 15 minutes with the same, okay? So the Poisson have to be every period the same. Regardless of how many people have arrived, that shouldn't change things in the future, right? So this usually applies, that's not be issue, but sometimes we talk about restaurant can be an issue, right? Because you can imagine that a restaurant has many people waiting along the queue, would likely to attract more customer. If you think that is important in your model, then you need to be using different model, okay? If you want to do that in the future, that actually requires to study 4,000 class in statistics. That is called stochastic process that will you study in the future how to, in those classes, how to do it. Probably you spend a whole semester to learn those. But for most of our application, that should be fine, okay? And another thing I do mention is if you imagine a restaurant, you have peak hour, non-peak hour, right? During the lunchtime and dinner time can be different from other time. So you should separate your modeling, right? If you do the modeling, lunchtime should be in one Poisson, right? And tea time another one, dinner time can be different. Other time will be different. So as long as separate them separately, should not be an issue. Okay. So that is the thing that I want to emphasize. Okay. And just this one give you this guy, the simplification. Just to remind you, E is nothing new but just a number. It's 2.713. And similar to all statistics in business, we never prove it, so this is given. Okay. If you try to prove, it becomes a stat class. I hint what can be, what might be the proof in the technical appendix. Okay, technical slide. So in case you want to look at it, you can look at it. But I'm not going to do any proof of that. If you're a QFN student, then probably you want to take a look. But other than that, you don't need to worry about that. Okay. It's not required for our class, but in case you want to study, this is the proof. Informal proof, not the real proof, but there's actually some idea why this is right. Okay, why there's a factorial here is anyway. I don't think many of you will be interested in that. But if you want to know, you can ask me. But I think there are already many things online to tell you why this is true. So last one is hypergeometric, okay? So this one is, I want to draw a picture because the picture will stick very well how we use it, okay? And this is the thing that I think is good to draw a graph here. So this is what we call hypergeometric sample with replacement, okay? So what N is here is the total number of stuff, okay? And you can imagine that you go, as an auditor, you go to a warehouse, right? Maybe they tell you that there's 100 items in the warehouse, okay? And out of which they told you that in the warehouse, okay, there's 30 of them are good items, okay? Okay, 30 of them, I'm not going to do 30, right? And that means, right, the rest of them, which is 70, say, for example, is the bad item. Okay, so this is the thing we know. Okay, so this is given by your client. We're not usually right to tell you this is the fact. Okay, and you want to verify this fact, or you want to do sampling. All right, you want to go there and check. Right, you don't, as an auditor, you have to attest. Right, you have to write, okay, this is the right. At least do some sample. Right, and how are you going to do that? All right, what we're going to do is you're going to take, I don't know how many. Maybe you got to take 10, right? 10 objects to check, right? And the question is, there will be, maybe I just draw here, right? There will be X of them is belong to the happy, right? And n minus x to then belong to unhappy. Okay, and of course, because you take things out of it, it really depends on which one you take, right? You take the blue one is happy, you take the green one will be sad. Okay, with happy face and sad face. Then this x, how many you pick, is a random variable, and this random variable follow a hypergeometric. Okay, that is the idea. Let me repeat what you're doing here. You can imagine this is you have a n very big n and big n items, right? Out of which a of them you consider successful, which happy face, and 70% n minus a is bad. Okay, and then you want to take small n out of it. Okay, then of course, how many of them are happy? I said depend on what you luckily drawn, because lucky draw there, all right? And the number of the good is x, right? And sad face is n minus x, and you're asking how many of them. Okay, and if you imagine that this is very useful to audit or quality control, right? So that's why I mentioned it, right? And you can imagine that I take n once and for all, right? I take n item out and check each one. Okay, that is idea we call sampling without replacement. We take once and for all. Okay, if we take it and put it back, and take it again and put it back, that is a binomial. All right, if I do it every time I take it out and put it back, and take it out, put it back, there's a binomial. Okay, but here I just take n item and check each one. Okay, and that is a hypergeometric. Okay, and not going to mention the formula. The P is like that, right? Remember, you give a distribution. The thing you need to know is the P function, which is this guy, and summarized by mean and variance, right? P is all the main function you need, right? It's a P function, but of course, the mean and the variance is a summary statistics, right? This is something that you would want to have. And just to remind you a little bit, is n, the big n is big enough compared to small n. That's no different. You can imagine that, right? The sample is very large. You just draw a small part of it. The sampling with replacement and without replacement is the same, right? With the pretty bad doesn't really matter, right? Because n is super large. Okay. So this example, right? This example, you go to warehouse. This is the example you do audit, right? And the question we don't ask here is, what is the best n, right? The question is, you do the audit, right? You go to the warehouse, they tell you n and a, then n is you decide the small n, right? And that is a part of the question, right? But this is not covered in the class. Second is, what should be the decision you want to make, right? You figure out that, suppose in this example, right, you got actually 2 defective. What should be the action? Okay. That is something we don't cover in the class, but the idea actually covered in the hypothesis testing. Okay, somewhat. It's like, if the probability of this happening is very low, then you will question what the client said. You will say the client may not be telling the truth. I'm not willing to attest to that, right? So the probability that given, assuming the client is right, if the probability happening is very low, then you will try to not attest. You don't have confidence. If it is within the reasonable range, then you're okay. And how to do it is not our class. Sorry. But that is a very important problem. How to make the decision rule, and how to choose the n, and how to the rule you try to say you are going to willing to accept what the client tells you. Okay, but that is not within our class, because our class is just an elementary class, and you will learn, right? If you learn everything in the class, then the school doesn't need to hire me, right? So there are many things you have to study in the future. Then that's why this class is a required class, right? Because you learn how to describe the future. Remember, what we're doing here is you learn looking from the data, make some assumption. This is how you quantify the future and how you make decision. Okay, hopefully that this class is very useful, because this is the we studies for 6 weeks, right? From now, almost 6 weeks. So that is the main thing that we want to study, right? Because probability modeling, how to do the model, right? And for the rest of the class, we will use the data to do further. But this is probability modeling is very useful, okay, by itself. Okay. And not going to look at the example. I think you can just look at it by yourself, and there's nothing very deep here. In case you want to ask me, and then we can talk about that again. Okay. Let's have a 15-minute breaks, and then in the meantime, you can ask me a question. I put up the U reply, and after the break, we talk about continuous random variable. Okay. So let's have a break of 15 minutes. In the meantime, I just open the U reply. After open the U reply, I go around to see if any question. Of course, you can always ask your question in the U reply. This is the one. Please do it during the break when you have time. So take a rest.
the same as the convolution. The convolution from suppose one candidate there will probably be of like half people coming. Probably one half, and someone comes.
So it's like
put a car.
Okay, so I have a restaurant. So 1 hour, there are 60 minutes, and then for 1 minute, like for example, 6.
Someone coming or not?
Yes.
It might be like half.
Might be like half.
Yeah, probably half. The coming one, probably not coming.
Yeah, so 45 they will come in, 45 they will not come in. Okay.
Then you say 1 hour instead of 2 hours. But what you need to write instead of 60 minutes, each minute
So what is the difference between costing it 60 times and
because you just say that and modeling how people come in. And it's for last. Yeah. And it's for last and this for the
So I toss a coin like 1/2 the time for 1 minute.
Yeah, something like that. When they get it out and then that is same as modeling something like that.
Oh, okay. So why do you keep a different
well we that's not this is example. The particle is this company is the end.
This one was similar to the other one.
It's the same. Yeah. This enable that's the book that's the photon guy.
Okay, so we say that this one, so for B.B. to first do video to calculate the this and calculate. That's what I need to know.
Yeah.
That's what I need to know.
Yeah, but then do you know is to model the number of arrival before the line. That's allocation. But I did say that because like your time. Okay, no population example. Population example. Okay, talk about population example. No, there's always stable definition. Example. When it's called data, it's example population. There's no data. The way it's defined as well. It's just a formula there. I don't know the different. You will also learn this 2 weeks later. We talk about sample and then you understand more. But at the moment, probability the variance is just the population. Because you can imagine how we get to be that just this infinite many times, then this must be a population. Because you imagine doing this so many times, then this will be population. That should be done. But the answer is it good? Because you can imagine that in your head, you toss a coin, million times. And my so doesn't get it. Anyway, so it's always yeah. But we do data, always do the sample. And you understand why we talk about this next week or the week after. You understand it by the end of October. If you don't understand, then it's a problem. All my problem.
Why upside down?
Oh, final is energy. And this is ideal, and we can put it down there. See this one.
So this is done there.
Oh, that's what we call line. The word point on this time. Just tell you this given was an average arrival rate. Okay. So you point the model with the process an hour. You can see on average how many people arrive in an hour. And it will be displayed like this formula.
Right. So
same as NP, that's an NP, right?
Yeah.
Same idea. It's small. And say that. Then you have this, I think, that will find out. Okay. But for example, on average, how many people come in? that the show. Like because you give me this, and I can tell you this combined. This tell the BP tell the large of that. I don't think anything is not. Yeah, you can. That's why I give it that assignment. You check out what going to be nice. What's going. It's very high, so I mean it's not something we have.
So that also I don't need to worry about that.
Yeah, if I don't talk about it, don't even worry about it. If you talk about that, you can know that. What's it called? Hey, you're done time. I got to make it up. I'm saying about your head. Yeah, yeah. Hold on.都在旁边有没有上课？如果不上课的话，还是不打那课的这种，就是那个不上课的，就在这个学费的，到底是比较的，我们有这种下课程的话，这个办法，反正错的话，影响关于放在这个课里头。因为讲讲很多做过电子化的，这个做比较快，就是我们还在要做快，这样，再做单，再主要就是我们上的话，我一直挺快，所以我还是发现那种对。其他班长讲，可能都会大家都，所以我在固定的没有后来也不因为如果他们不习惯的就是其他班想我的比较所以老师教的比较开心，
I trust on 3 times. What is the possibility of me getting to X, for example? So this is like an tail and tail have different.
I know it's the same. I know it's just total number of them.
They're just the same. Yeah.
For final. So what about for other things? For other things, well, final will actually just kind of number. Okay, and then so that's what we can.
Yeah.
But sometimes you can, right? If you care, it's different. It's not final, it's other thing. Final, we just don't care about the order of. That's the sort of the same. And if you care order, then it becomes very complicated.
Oh.
Many times you care, right?
Yeah.
So I hope you still survive. Some of you during the break said I'm too slow, need me too fast. But I guess it's I mean, for sure, no matter what the speed I'm teaching, it is always some people feel very fast, some people will feel slow. And I actually learned from my people who actually got a teaching award. He always told me that actually that's good. It's optimal to catering the mean or median is good. It could be good. Some people feel it's very fast, some people are slow, then you're the right speed. If people think you are very good speed, then actually you're actually too slow. If everything is too fast, then of course you're too fast. So I hope I can make happy. See, already say some people want, can I talk slower? So you can see I can assignment template. Oh, it's fine. I think it's fine for this time. Next time you try to follow the template because in that case the TA can grade easily. This is TA. I shouldn't be an issue. The weather is bad. Yes, that's true. Yeah, today if you know that. But let's see. Okay, everyone agrees, rainy. I guess there's no Poisson. Yeah, math is hard. For sure, math is hard. But do note that the main thing is we learn how to do modeling. So we don't really actually do the calculation, but later you learn, probably after the next class, we will do Excel. Then probably you learn how to do those. And hopefully when you do the assignment, you will learn a little bit more how we do. Yeah, the difference of hypergeometric binomial is hypergeometric is you just do sampling without replacement. You take n item once and for all. Okay, and binomial is where you would every time you take and put it back to it back. So you don't consider the effect. You take n once and for all. You take one and one and one. Okay, so that is the difference. And of course, if you look at Wikipedia or other statistical, they will give you many type of distribution. But I think I just want to focus on the one that introduced in textbook, and that is very common. Then you can actually, from the knowledge we learn, can generalize to more. But we just focus on the thing that cover in the usual. So I think now we are on the good speed because the median and the mean is actually say I am okay, then I think it's the speed is correct. Of course, I can be slower, but I think that is something I always feel for this class is important to do assignment. Okay, it's important when you try to. That's why I put this assignment early. While you have any issue with the assignment, please feel free to find our TA. He's able to help you. But of course, I guess most of the question actually you can look at the example. It shouldn't be an issue how to do it. Okay, all the slides should be fine. But if you do really need help, do really make an appointment. But it's good that you would try to. So same lecture, I think today. I mean, again, there are some people don't think it's easy to follow. Then please try to do the assignment. Or if you still find difficult, look at the lecture notes. There are a lot of exercise there. You can try to check out how I do them. Hopefully that will be making you less anxious. Yeah, statistics not easy. I mean, to be honest, I mean, many of you know I'm an actuarial undergrad. So basically, my 3 years in the college is basically study statistics. So it's not that easy. I mean, I'm pretty sure you need some exercise that is like other math. And the good thing about the introduction is that it's very applied. So there's no proof in here. So basically, just look at the example, hard exercise, and try to see what can be applied. And you do projects so that hopefully that will make you learn a little bit more. What happened if you type your keyboard so fast? Oh yeah, that's fun. So what does that mean? But it's interesting. I hate raining. So many question assignment. Unfortunately, yes, it tries to force you to work on it. I mean, the assignment by itself is trying to make sure you understand. So if you think that you need more time, let me know. We can extend the deadline. That's not an issue. So maybe I can ask you again. Next class, tell me whether you need some extension. But it's not due yet, right? The assignment is not due until next one. So assignment will be a lot. So shouldn't be an issue, but it's still hopefully it's fine. If you don't know how to do assignment, please talk to TA, see if he can help you. Okay, or you can ask your classmate, because although you should submit your own homework, you feel free to talk with your classmate. This is one thing you need to learn. Okay, hopefully it's too cold. Yeah, I think it's a bit cold. That's true. So I hope that should be fine. So continuous random variable. I'm sure that some of you actually feel very difficult, but with some exercise, I hope that will increasingly getting easier. Because I guess up to now, things are new if you level up probability. Okay, pretty new. But from now on, we look at the knowledge. The term is similar. From now on, it's always the same thing. So hopefully, with that, your life will feel less miserable. I mean, for sure. I mean, learning math is always require exercise. Okay, it's always need example exercise. There's no shortcut to that. Just like you learn music instrument or learn swimming. Okay, the teacher teach you what to do. You have to go home and practice. Okay, it's not enough to just go there and just listen. Okay, so that's why assignment is very important part of this learning process. If you don't do it, you can't make it. Just like if you, I don't know whether you go to data camp. You go to data camp, you try to do R and Python. If you don't really just look at it, you couldn't learn. Talking about R and Python, so just remember we have a I think the Python makeup class optional, which is 2 weeks after this week. You feel free to attend, or if you don't, you can just watch the video. There's I think Tuesday and Wednesday, you can attend either one of them. And some of you actually told me that they want to learn R Studio, so R as well. So, but R, the one problem of R is that you can't easily work with your iPad. So in order to do that, we will make a B.A. lab. We'll put a B.A. lab, and that will be we will do it there. Of course, it will become optional. So we'll cancel some of the class here to make you go there also optional class. So we work out over there. Okay, probably at the end somewhere in the November. So we will probably cancel the next Monday class and some other class to make, because if I add extra class then you'll complain, right? So I mean, because the reason why we don't do it here, because you have to bring your laptop and always in pain. So we'll make an optional class in the lab. Then you can attend or not attend, doesn't matter. Usually I would do it at night, so that's why then to maximize the chance you can attend. Or again, I will make 2 sections. You can either attend one or either. Okay, of course you can always skip it because it's optional. Okay, the only thing you need from this class is Excel. Okay, but if you want to learn R or Python, please feel free to attend. And so continuous random variable. Okay, so for discrete it's very simple, because the number you assign or the uncertainty you assign is a number. It's an integer usually, right? Then you can count them. You can have big P and also big F. It's something simple, right? Because you can easily, like this, you can draw a bar chart, right? Remember, this is the 2 outcome, head or tail, right? That is very simple, right? You can imagine this is how can from big P to big F, right? Similarly, you can also, if you have 3 outcome, right? You can also know from the big P and big F is easy, right? But what happened when you divide it into many outcomes, right? Suppose you have here, right? You have 1, 2, right? 3, 4, so on and so forth, right? And this become much smaller. Each one equally likely, right? Become much smaller, right? So this one will become smaller, and smaller, right? More and more outcome, and this become very small, right? And then the problem would be how can you define this, right? Because when you have many outcome, right, and this a lot, then it becomes so small, right? Because look at this, if equally likely uniform, each one is 1/n, right? When n is very large, say infinity, this becomes 0. P is not well defined, right? But this one is well defined because this is just stacking thing, right? This is still well defined, right? This is still a line over there, right? So that's why the idea of continuous for F is well defined easily. For the P is not really it's not easy to define properly. Okay. And we can still well define the probability x less than something that is well defined, right, for the continuous. But how do we define the left-hand side one, right? The idea is the same, right? We can define this as a small f, right? You can imagine this is flat. You can imagine there's something flat as well, right? And how do we define f and big F? Maybe I draw another slide. Okay, graphically this looks like this. How we define f and in continuous. Okay, remember f is same as f of x, right? Is equal to probability that x less than or equal to x, right? It's small. So that means that I coming from, so I just draw an F here. Okay, I have number A here. Okay, and the height, of course, is f of A. Okay, and this should be similar to what we learned in the P. Is the following. F is something like this, suppose. I don't know, maybe bell curve. That would be a good idea. Okay, and suppose A is here. What is small a means? The small f means is the following. So same as what we learned from the P, okay? This is just the height. The area become this height. And this area is this height. And this area is this height. And let me use the black. Okay. So for F is well defined. So F and big F and small f, how they're related? It's actually same as big F and small p. Okay. The small f is defined as, okay, every height is at this number. Looking at this number, look at the area before it, same as p. Okay. This is what we call the density function. Okay. They call probability density. Is defined reversely. We define big F looking at the probability, f of A is probability that the random variable is less than or equal to that number. Same as the discrete version, right? The discrete same meaning. The discrete, we learn the stacking the probability, right? And how we define discrete is we have a big P and stacking the P become big F. Okay, fine. Now we continuous, we don't start with the big P. We start with the big F. And from big F is unstacking that become the F. Let me repeat, right? Discrete is you have the P, you keep stacking the P, become the F. Okay? Same here, but we reverse. We define the big F and unstack, okay? Then become the F. Okay? But that F become a density. It's not probability. The reason is because when you're continuous, the probability equal to that certain number will be 0. Why? Imagine the case. I just try to, suppose, do football or soccer. I try to kick the ball, right? Trying to hit the goalie, right? There are many, many different areas I can hit on. I exactly hit on that number will be 0. Okay? Put it in this way. Suppose there's Hansen index. You try to predict what is the Hansen index, exactly number, will be very hard. Right? Or exactly guess what's the temperature now is very hard. Right? Maybe you may think, okay, it's very easy. Isn't it either 25 or 26? No. It is maybe 25.3261306.100111, right? It can be the real thing, can be very long decimal. Exactly guessing the right one will be 0. Right? The same idea here, right? Continuous. So exactly you get the right thing will be very difficult. Okay? So that is F and big F and small f. But you can imagine that's no different from the P and there's no different from P and F, the same idea. Okay? The reason that we have to be very careful is because of the idea, the tools you want to use it. Here, actually, we don't talk about it. Find an area is actually called integration. Okay? If you learn calculus, that is the way to do it. Calculus is integrate. The left-hand side become right-hand side. And your differentiation, you go to the right-hand side to the left-hand side. But I'm not talking about calculus in this class. But we'll use the idea of area. So what you know is, for our class is area under the small f, which we use all the time, is the area. Okay? Okay? Basically, there's something unique in this class is the following. If I have a small f, this x, and this is the A to B, and this area is the probability that x between A and B. Okay? And it's written as f of B minus f of A. Okay? First thing, the area under f is this probability. I think that should work. This is something you should remember always. Okay? And second, why this is true? Because this guy is what? This guy is looking at the area before, right? Or the area before is this guy. And this f of A is probably less than A, right? So this area. So you subtract, you say kindergarten problem, black will be the golden minus green. Okay. And this is the one that we often use it. Okay. We use it for the rest of our course. We rely on this because we look at the bell curve. There's something we often use this formula. Not formula, but I mean this representation. Okay. Just to remind yourself what's the thing. The area of the F is the probability. Okay. Let me repeat once. The area of the F is the probability. Okay. Let me repeat. The area of F between A and B with the probability between A and B. Okay. That is the thing we require for the rest of our course. We'll do it again. So don't worry, you will do it. You will understand because we will be doing for the rest of our course. So you can't miss it, but that is the thing we need. Okay. And of course, you do notice the complement rule also will use it. Okay. If we are trying to look at the area of, maybe I draw in the graph. Is it okay to move in the graph? Very often, another thing that you will be useful is I have an F here, suppose, right? And if you want to find this area, how do you do that? It just, for this A, this 1 minus F of A. The reason, complement rule, total area is probability must be 1. Left-hand side is FA, right-hand side is F of A. Is that clear? So I think these are the things that you will be, you'll be useful for the rest of our course. But don't worry, you will be doing this many, many times, so you can't miss it, okay? So don't worry about it. But just, this is the thing that you don't need to, I want to mention it upfront, is because some of you worry about calculus integration, will just become anxious. So, but don't worry, this is something we need, okay? That's something you need to know. Is that clear? Okay. Is that clear? And you can imagine F is same as the big P, right? Because if you try to draw, you just convert in your mind, this is the bar chart, same thing. Okay. In your mind, you convert this as a bar graph with the same idea. Because the area is the probability, so same idea. Okay. Now let us go back to the this one, okay? The definition. As we said about the integration, although it's not required, so this is not required, but if you understand, that is integration idea. It's area on the left-hand side, integrate from infinity. And that's why the F, using the calculus, this is integration and differentiation, okay? If you don't know, that's fine. You don't have to know it, okay? But this is something that probably you want to notice is this F, intuitively, is a probability. Why density is because it's asking the X, like equal F of X is X plus some small number over that one. So it's called density. So that is the idea. If you learn physics, this is a mass and the density, that is the same idea there. But we are not doing physics, we are not doing calculus. So in case you learn from that, you would see what it means. But if you don't really worry about it. It just gives you probability under the area, okay? Because integration is the area. So that's why we also work on this one. And we look at area is because of the idea, okay? Unfortunately, this is the usually we do. So later you will see, so don't worry about that. Okay. So one technical point I want to mention is when you have continuous random variable, I have mentioned already, probably equal to the certain value will be 0. Okay, because to guess exactly that number will be exactly 0. Do note that 0 doesn't mean impossible. Okay, 0 just means that it's so small that we can't put any number there. It's still possible because you always ask, okay? If everything is 0, then what number is possible? Okay? But 0 doesn't mean impossible. It means it's so small you can't say exactly this. It's some philosophy question. Even 1 doesn't mean always happen, right? It doesn't mean that it happened with probably 1. Okay? There's some, if you learn philosophy, you will learn probably 1 doesn't mean always happen. It's almost sure happening. So that is technically there's a 0 and 1 is not exactly always happen. Just like the following. If a ruler, okay, you can measure the distance of this object, your up or your hair, whatever. You can use a ruler, no matter how small. But you can't measure the cell. You can measure atom. So the ruler you use is so large that everything becomes 0 at that point, right? But you know cell or germs or virus have length. But you use a normal ruler, you cannot do it. The idea is you use the probability 0 to 1, and when you're talking about the thing you talk about, it's a 0, but doesn't mean that they're not possible. I hope that, you use a ruler to measure the cell is 0, but it's still there. There's something there, okay? So I hope that answered, but to understand the right way, it's beyond our class. You should go to philosophy and understand probability. So, but I just want to emphasize, in your mind, you may be thinking, whatever, but there's something there, okay? And I'm not going to detail here because the definition involves integration, but the same idea goes on. Mean and variance is asking us if we repeat this experiment many, many times. Every time the number there, average of those number is mean, right? Deviation from that would be variance, and then the number, right? Same as the discrete version, okay? Because we can't really write it in the summation form because they are continuous. They have to be written in this way. But that's no different from what we learned. So nothing for something more difficult. The calculation wise difficult, okay? But we are not asking you to do any integration, okay? The reason that I can't black it because I have to define it, right? So if I say black, then say I don't define, but you don't have to know the integration thing, okay? But that is the meaning. So now I think I still have time to talk about uniform and exponential. The next class not normal, that would be fine. The two things that would be probably we have some time to talk about normal, but I don't know. But first, let's talk about uniform. Uniform is usually the way that how you would able you to translate your knowledge from discrete to continuous. Okay, uniform is very simple. Just say the idea is the value is likely between A and B, and this is very normal, right? And that usually what you expect to understand when you look at the TV. The finance TV is asking an expert, what is today's stock price? Hence an index, right? They will say it's between A and B, right? And how to interpret that? Usually he means uniform between A and B, right? It can be as low as maybe 15,000 to 7,000, right? Then that is the prediction, right? Then that is, don't say anything, right? Same as what you learn from the discrete. When you don't say anything, then it's uniform, right? And uniform you can expect, right? Actually, from the idea, you can imagine the F should be a flat thing, right? Because that is following from the idea of the bar chart, right? The discrete version is a flat bar chart, right? If you remember, if you look at the discrete version of the uniform, it's like this flat, right? Right? And if you same idea extend, it's just a flat curve, right? And second thing I want to mention a little bit is the area under this curve must be 1, right? If I mention correct, this must be 1, right? This area must be 1. Why? Because this probability, right? The sample space is A to B, then this must be 1. And that tells us how is the height. Remember, the area is the probability. Area is 1, right? So the base is what? B minus A, right? Use your primary school math. Rectangle is what? Base times height, right? Or width times length, right? So it's this times this. This is B minus A times what is 1. It's inverse, is this guy. So that's how you get this one. Okay? And of course, Either you can use integration or you can use, the idea is, suppose I look at this particular x, right? And what is this area, right? This area is actually the f function, right? First, you can use math to tell you, and repeat the primary school math, okay? What is the area? Will be the base times height, right? Base is x minus a. Height is this one, right? So this graph is x minus a over b minus a. So this is how you get the formula in the previous slide. Check what's a big F. This is the formula. Of course, you can do integration, but that's the idea, right? And this linear in a, linear in x, right? So this is go up, right? Because when x is a, this is 0, right? And x is b, f is 1, right? Can you see that? Right? This formula. When x is a, this is 0. When x is b, this is 1. So that's how you get this 2 point. And this linear, right? So it's a line. Is that clear how you get that? Of course, this is not math class. I'm not expecting to reproduce this. I just put it there for you to know how it looks like. Okay? So I'm not expecting you to know how to do that, but of course, although I said you don't need to know how to do it, but I am expecting you to know this formula, right? Right? The formula, of course, but knowing means you know where to find it when I ask you, right? So you see the example what I'm asking, so don't worry. Let me put the example because you will see what I'm asking. Because, but before that, I give you the mean and variance. Why I care about that? Just a repeat. Because I heard some cough noise, but it's not me. I'm not coughing. Scary. Anyway, so this mean and variance. Mean and variance is, I again telling you this is representing the f and small f or the big F, right? You want to have you tell me uniform, then maybe very complicated the graph, right? Then you probably want to tell people this is the mean, this is the variance, right? Mean is just the center. You expect this formula would be a plus b over 2, right? Actually the center, right? Because look at a plus b over 2, right? Because the lower point is a, the upper point is b, right? The middle is a over b, a plus b over 2, right? Is that clear? Because here is at the center, right? Midway. And the variance will be b minus a, which is a range, square over 12, where y is 12 and 12, not our concern. For those who learn math, do the calculus, then you will see. I'm not going to explain anything about that, okay? Because we just take it as given. Of course, you can calculate it, and there's no particular reasoning why you have 12, but b is a range square. It makes sense, right? The larger the range, the variance larger, right? The further then I'm not going to explain. Okay. This is the graph looks like, but I guess it's important to look at this one. I think this exactly fit the idea of today, right? You want to look at the rainfall, right? The rainfall can be modeled uniform from 1 to 4, okay? The question would be what's the mean and what is the variance, right? Because you actually know the future is modeled as a uniform from 1 to 4. Actually, you know everything, right? So the question is, I want to know further. Can you give me a number that represents this? That's the mean. How accurate is the variance? Then just apply the formula, then you're done. Because A is 1, B is 4. It's very simple, very direct, right? Nothing new there, right? As long as you look at the formula, that's it. I don't think I need to talk more, right? This is a plug in the number. Okay? Any question? So here comes a more important part, and this is the part that I want to emphasize on, and because we actually do a lot of this question from the second half of this course, is looking at this kind of question is I follow uniform from 1 mm to 4 mm, then I want 1 to 3. So the idea is following. So if you look at the F graph, I think that is the most convenient look at this is 1 to 4, right? And you know this is what's the height? It's 1/3. I hope it's clear why it's 1/3. Because the base is 3, the height must be 1/3 to make it 1. Right? Is that clear? Now, the question would be, what's probability 1 and 3? So that's what the question is like this, right? 1 up to 3 is this area, right? Because area under the curve for F is the area. Sorry, the probability, right? The area, let me repeat the F, right? What's it? Small f. Small f is area under the small f will be the probability, right? So as long as I draw the F, I can calculate area, then I'm done. Okay. And one way to do it is look at the area, right? The area, the base is just 2, right? 3 minus 1, right? So that's why it's 2 times 1/3 is 2/3. That's it. You're done. That's how you get this one. Let me repeat, because it's so simple, it's so fast, and some people will just don't know what I'm talking about. But the area is the red area, right? Red area is a rectangle. Rectangle is base times height. The base is 2. The height is 1/3. So 2 times 1/3 is 2/3. So that's it. No more. Got it? Because some people are still confused, but I hope that's not something very difficult. But again, you can see there's another way to do it is look at exactly how we do this guy. Right? We can rewrite it as 3 minus 1, right? Because this is the way we do, right? Just look at the thing on the left of 3 and minus the left of 1, right? And left of 3 just f of 3, and left of 1 is f of 1. Is that clear? Okay. And this applying the formula directly. Okay. The reason why I have to talk about in this way, because only you can do uniform easily by current area. But otherwise, you have to rely on this F formula. This F usually compute from Excel, so don't worry about that. Excel gives you the idea how to calculate, plug in the formula, you get the F, and just do subtraction. So we will do this all the time in the future, but this is the idea, to calculate this probability. Okay? I hope that is clear. So don't worry, you do assignment, then you see. Okay? That is something that you will never miss, don't worry, because we're asking the same question again, under different context and only. Okay? So this is again the same question, but again 2 from 3, right? So you should then be, even if you don't completely convinced, right? This will be the right X and F, right? 1 to 4, and this is 1/3, right? And then you're asking 2 to 3, right? Right. So that's why the base is 1, the height is 1/3, so it's 1/3. Right? Of course, you can do the calculation. Is that okay? Of course, you can calculate the area on the left of 3 minus area left of 2. That's what it's doing, right? Because what is F? Big F is area on the left, right? So F of 3 is area on the left of 3 minus area left of 2 with area between 2 and 3. So there's nothing new, but something you learn in the kindergarten, right? Any question? Know that if know that I have I can talk about this. Okay, shouldn't be a big issue because this is closely related to learn the Poisson. Okay, I will talk. I say one sentence, then you understand it's not difficult. So remember, Poisson is what? Poisson is the idea that, say, within an hour, how many customers come in, right? And we just count the number of people come in. Poisson is saying, how long does it take before a customer come in? Okay, so let me draw a picture that will stick in your mind, because I think always drawing a picture will help understand a lot of stuff, right? So if you remember, Poisson is asking, say, suppose 0 to 1 hour, right? And we cut it into very small minutes, right? And then we're asking, okay, some people come in here, some people come in here, some people come in here. Poisson is looking at the random variable that is recording number of people come in this hour. Is that clear? Now, exponential is closely related, just asking how long does it take for one guy to come? So it's exactly asking this question. How long does it take for the first guy to come? After the second guy, how long does it take the third guy to come? And the same idea, right? Because remember, Poisson has no memory, so all of them are the same. You don't have to worry about it. Just to count, how long does it wait for the first guy to come? That's it. Okay? Or after the first guy, and then how long between one and first and second to first, so on and so forth. Okay? How long does it take for a guy to come? Okay? Assuming you are looking at Poisson problem, right? The same idea. Okay? And we said, okay, I'm not going to prove anything, but I'm going to claim, I'm sorry, but that will be how long does it wait? It looks like a Poisson. Okay, it looks like Poisson in this, or the F looks like this. So it will be looks like something like this, exponential. Okay, so you will look like a slope going down, right? The F function. Okay, and why it called exponential? Because this is an exponential curve, look like this, and the area on the left is this formula. Okay. So you don't need to worry about big F, small f. The big F is something you need to care, right? Same as the discrete, right? You remember the big P, you don't worry about big F. For continuous, you don't worry about the small f. You won't want to remember the big F, right? The big F will do all the calculation for us. Okay. So one thing that I want to mention, something probably will end today's after talk about that, is what is the mean and variance. Okay, I want to explain the mean. It's very simple. Mean is just 1 over lambda. Why? Actually, it's very intuitive. Let me explain in the graph again. Okay, that's the main thing I want to explain. Okay, consider the model. I have an hour. Okay, I Poisson lambda is 2. Okay, lambda is 2 means that on average, I have 2 people come in. Okay, what does that mean? It means that the following, right? I have expect 1 people come here, 1 people come here, right? So every 1 guy would take what? Half of an hour or 30 minutes, right? To come, right? But what is 1/2? It's 1 over lambda. You take 1 over lambda at a time to come. Is that clear? Right? Because you have expect 2 people to come in, so you expect 1/2 of the hour for 1 guy to come. Okay, so that's why 1 over lambda. And the variance, do integration yourself. You want to care, but that is what we have. I'm not going to explain that one. Okay, is that clear why we have that? Okay, and we'll talk about the example next class. But you can see if the waiting time for customer to arrive is 20 minutes, right? And then you can do all the calculation. Okay, we'll talk about this again next class. Don't worry, we'll talk about this on Thursday. So I hope you have a safe the rest of the day, because I think still the red storm is going on. So stay safe. I'll see you on Thursday. So next Monday we don't have class because we will make it up for the in the optional hour class. So don't worry about that. So we'll book the room, and then we'll do the optional hour class in the B.B.A lab, because many of you have the iPad, so we have to do it. Okay, I'll see you. Stay safe.